This first video will be a recap of our introductory topic to thermodynamics, which is the very last thing we covered before chaos took over. So as you may recall, back in 123, you talked about enthalpy, which is one of the thermodynamics concepts we will talk about. Enthalpy has the symbol of H because enthalpy is about heat energy. So hopefully you kind of remember that a little bit. This first concept we will talk about is entropy, and I will apologize because it's very hard to get those names right again and again. Entropy has the symbol of S, and S is the spread of energy. So enthalpy and entropy and Gibbs free energy are all part of the things we will talk about in our thermodynamics unit. So what we're trying to do when we talk about all these thermodynamics things is trying to predict whether a reaction will happen or not. And the chemistry word for whether a reaction will happen or not is spontaneous. So we all know some natural phenomenon that happens spontaneously, that naturally occurs. Rain falls from the sky because gravity causes it to. So in these reactions here, could you imagine that solid sodium chloride, table salt, could you imagine that spontaneously becomes sodium solid and chlorine gas? I doubt it. So that reaction, we would say, is non-spontaneous. A chemist would say that reaction is non-spontaneous. If you look at the second one, in the second one, we say solid glucose reacts with oxygen to become CO2 and water. And I bet a lot of you know from biology classes that that reaction does occur naturally. Sugar is broken down into CO2 and water. So a chemist says that reaction is spontaneous. What a chemist means when they say spontaneous or non-spontaneous, what they mean when they say spontaneous is that K is large. So hopefully you remember K. That's our equilibrium constant. And that equilibrium constant, remember, we hope, is products. The concentration of products multiplied together raise their coefficients over reactants. So hopefully that K is still familiar in your brain, but we say if K is big, that means the amount of products is big, so the reaction happens naturally. The reaction is spontaneous. So there's the K for that top reaction that we said is non-spontaneous, -35, that's pretty small. There's the K value for the reaction we did say is spontaneous. It's pretty big, 10 to the 350th power. Pretty good, yeah. Okay, so if you go back to what you talked about in 123, where you talked about enthalpy, would you say this reaction is endothermic or exothermic? Hopefully you see that negative sign right there and you say negative, that reaction is exothermic, so heat is exiting that system. In general, exothermic reactions are spontaneous. I don't expect you to know already that this reaction is spontaneous, but it is. This reaction is spontaneous. That second reaction, that delta H is a positive value, so that's an endothermic reaction. And in general, endothermic reactions are non-spontaneous. That's the exact same reaction we saw on the previous slide. Here's the same reaction we saw on the previous slide where this reaction is a negative delta H. That's an exothermic reaction. And in general, exothermic reactions are spontaneous. Is that the truth, that all exothermic reactions are spontaneous and all endothermic reactions are non-spontaneous? Not at all. Because as it turns out, this bottom reaction is positive delta H, so it's an endothermic reaction. However, this reaction is spontaneous. So that leads us to know that endo and exo, enthalpy, is an important factor when determining spontaneity or non-spontaneity, but it's not the only factor. The other factor to consider, we will say, is entropy. So entropy is the spread of energy. Energy tends to spread out on its own. So you see all those little gas molecules trapped over in the bulb on the left. If you open that stopcock in the middle, hopefully you already know that those gas molecules will spread over the entire system. That energy spreads out naturally. Entropy is spreading out of energy. So that's a spontaneous reaction for that stuff to spread out. Could you imagine that you have all of them all spread out and spontaneously they will accumulate back in one side bulb? I don't think so. They're always going to be dispersed as long as they can be dispersed. So anything that results in a more concentrated energy, the entropy is going to go down from reactants to products. So we've said it again, we've said it before, we'll say it again. Entropy is the spread of energy. That's why we give it the symbol of S, which is kind of nice and convenient. We don't always have good reasons for our acronyms. So we say that amount of entropy in the products, the final amount of entropy, is greater than the initial amount of entropy because the entropy is more, the energy is more spread in the products than it was in the reactants. That would be a positive delta S value for that reaction. Positive delta S. So anytime you're seeing a phase change from a solid to a liquid, hopefully you recognize that liquid particles are more dispersed than solid particles. So liquid entropy is greater than solid entropy. And continuing on, gas entropy is greater than liquid entropy. So increasing entropy depending on state changes, phase changes. Yep. Anytime you melt ice, that's going to be a positive entropy reaction. The products have more entropy than the reactants. So entropy is a state function. What the heck is a state function? A state function says it doesn't matter how you got there. It matters that you start and end in the same place. So if you're climbing that mountain and take the blue path or the red path, you might have extended a different amount of work, but the energy change was the same from the beginning to the end. So energy, enthalpy, pressure, volume, temperature, and entropy are all state function. Doesn't matter how you got there. It matters that you start and end in the same place. So if you may remember from enthalpy reactions back in 123, the enthalpy change for a reaction is the summation of all the enthalpies of the products minus the summation of all of the enthalpies of the reactants, multiplied by their coefficients, of course. So the exact same calculation is done for entropy reactions, entropy of reactions. So the summation of the product of summation of the entropy of the products multiplied by their coefficients minus the summation of entropy of the reactants multiplied by their coefficients. So there's a standard generic thing, but that doesn't always mean so much to us. Let's do a real example. So if we look at that given example, 2CO gas plus O2 gas yields 2CO2 gas. The actual physical states we've ignored sometimes previously. That's unfortunately important for all this thermodynamics stuff because the entropy of a solid is very different from the entropy of a liquid and a gas. So make sure that you include that. So if we're wanting to calculate the delta S of this reaction, we would say it's the summation of 2 times the entropy of CO2 minus the summation of 2 times the entropy of CO. I wish I'd written this differently, but it's too late now. Plus entropy of O2. So 2 times the given number for CO2, which is 213.6 joules per kmol, minus 2 times the number for CO, 197.9 joules per kmol, plus 205 joules per kmol. I didn't need that one. Whoops. So delta S of the reaction, at this point, it's just a plug and chug. And hopefully if you sum that, you get the same answer that I do, which is negative 173.6 joules per kmol. So that negative is an important thing to point out for your entropy value, entropy of the reaction. That means the system became more ordered as the reaction took place. So hopefully that's kind of intuitive. You went from 2 moles of gas plus 1 mole gas. You went from 3 moles of gas to 2 moles of gas. When you go from 3 moles to 2 moles of gas, yep, you're creating a more ordered system. So entropy change for that reaction is negative. So you need to be able to calculate the actual quantitative value like we did here, but you also need to recognize that when you look at that reaction, you need to be able to predict the sign of entropy for a given reaction, knowing that you go from 3 moles of gas to 2 moles of gas. So back to the PowerPoint. So if we so many clicks. If we, yep, that's our math. Hopefully yours matches. Excellent. If we look at some standard reactions and we try to decide just by looking at the sentence if that reaction is positive or negative delta S. Condensing water vapor. Condensing water vapor means going from water as a gas to water as a liquid. So which has more entropy? Gas has more entropy, so the reactant will be a higher entropy value. So if you do products minus reactants, you're going to get a negative delta S for that reaction. Your entropy is decreasing as that reaction takes place. So yeah, that says Q is less than 0. So heat has to leave that system. We will talk about heat energy, enthalpy stuff later. Q is the symbol for heat. Yeah, we'll talk about it later. So if we talk about forming a sucrose solution from crystals of sugar, that's solid crystals of sugar becoming aqueous crystals, aqueous glucose. So you're taking that solid, and that solid is separating particles. It's not dissociating, but all the little particles that are packed closely together in the solid, they're separating and becoming solvated by water molecules. So hopefully you can recognize that solution, that aqueous solution, is going to have a greater entropy than the solid crystal structure did. So that is a positive delta S for that reaction. If you heat hydrogen gas from 60 to 80, it's a gas before, it's a gas after. But a hotter gas has more spread out energy than a colder gas. So there's our gases with little vectors to show their motion. So if you are at 60 degrees on the left and 80 degrees on the right, this vector, if you look at that one in particular, this vector is longer for this particle than it is for that particle. It's got more energy moving. The spread of the energy gets bigger. So at the lower temperature, you have a taller curve that is more narrow. At a higher temperature, that spread of energy, you've still got the same number of molecules, but you've got a spread out of your energy. Your curve gets wider. So that has more entropy when your curve is wider because your spread of molecules is greater. Entropy is positive for that reaction because your reactants have more, your products have more entropy than your reactants. So if we compare these two things, the molecule on the right has 6 carbons and 6 hydrogens. The molecule on the left has 6 carbons and 6 hydrogens. The molecule on the right has 2 carbons and 2 hydrogens. Anytime you have more atoms, you're going to have more spread out energy. So comparing a single molecule to a single molecule, more atoms means more spread out energy. So the molecule on the left has greater entropy than the molecule on the right. There's our actual values to prove it. However, That was comparing a single molecule to a single molecule. Down in this bottom example, we're comparing a single molecule to 3 molecules of this other type. So our total number of atoms there is actually the same, but that doesn't matter. 3 molecules versus 1 molecule, 3 molecules are going to have more spread out energy. Mathematically, if you wanted to find out what the entropy of this stuff is, you take the number of one of those molecules and multiply it by 3. So this guy has way more entropy because there are 3 molecules of that type rather than the single molecule.